So what I want to do today is I want to talk about how to estimate certain integrals. So what is the main thing you're trying to do when you estimate integrals? This is a straightforward question. What are you trying to do when you estimate an integral?
Find the area of the curve.
Find the end of the curve, but why are we estimating something rather than calculating it exactly?
It's really hard.
It's usually really hard. That's one reason. There's another reason in addition to being really hard. Yes?
Computers can't do continuous processes.
No. I mean, well, that's irrelevant. It's like I won't root for the Yankees. That's a true statement, but it's not going to. Yes?
We're really lazy.
It's very close to being really lazy. Sometimes it's fine to be lazy. You know, the fact that we're lazy is a given. But the fact that in many problems we don't actually need to know the value of the integral. We just need to know approximately how big is it, right? Because for our purposes, if it's an error term, we just need to know it's smaller, we need it goes to 0. We don't need to know its value exactly. So I want to talk about approximating integrals. I don't know if I've given you this example yet. Imagine somehow my financial situation takes a drastic change for the better, and I now have the resources to give you $1 billion. How do you feel? This should not be a hard question, guys. How do you feel? Good. And now I tell you, unfortunately, for God, you're going to have to pay a little tax on it. You're going to have to pay $1 million in tax. How do you feel?
Good.
Good. Yes. Does the $1 million really matter if I'm giving you $1 billion? No. Okay? If I'm only giving you $10,000, yes, the $1 million would matter enormously. But the billion is so much larger than the million just doesn't matter. There's no reason to obsess about trying to get the exact value. Are you going to pay $1 million in taxes, $500,000 in taxes, $2 million? Anything around that size, you're not going to notice relative to $1 billion. It's the same thing with these integrals. We want to know just approximately how big are they. So a big one we want to integrate is the integral from, say, the absolute value of x greater than or equal to sigma to the 1 plus delta e to the negative x squared over 2 sigma squared dx 1 over square root of 2 pi sigma squared. So this is the Gaussian integral. You know, this is the Gaussian density, and I'm looking at all the stuff that's in some sense deep in the tail. And so if you want to just plot what the Gaussian looks like, you know, I've drawn it so it has mean 0, variance sigma. So approximately, maybe this is 2 sigma here, negative 2 sigma over here. And sigma is the standard deviation. It's how far I measure things. I'm going for x greater than or equal to sigma to the 1 plus delta. So that means sigma to the delta times sigma. So it means the number of standard deviations is of size sigma to the delta. So if you know Chebyshev's theorem that says, you know, the probability that a random variable takes on a value a certain amount greater than the mean, you measure things in terms of the standard deviation. We are going very far relative to the standard deviation. Instead of doing this, we could instead look at something of the form sigma times g of sigma if g of sigma tends to infinity. That's the more general type of integral to look. It's the same techniques to handle either one. The idea is I want to be a large number of standard deviations away. So if large number of standard deviations away, the integral should go to what? Integral goes to what? Goes to 0. And then the question is just how rapidly does it go to 0? When you have something like this, you always want to change variables. You want to make things more natural. So the first thing is, let's change variables. Let's let w equal x over square root of 2 sigma. And the reason I'm putting in the square root of 2 is just so that I now have e to the negative w squared. All right, so now I get it's going to be the integral, and now I'm going to have w in absolute value is greater than or equal to, so I have sigma to the 1 plus delta. All right, so maybe the square root of 2 will make things a little bit annoying with the bound. So maybe I'll keep that. So I'll just have now, this is going to be what? W will be greater than or equal to sigma to the delta. Because if x is greater than sigma to the 1 plus delta, then w is going to be greater than sigma to the delta. I now have 1 over square root of 2 pi sigma squared e to the negative x squared, e to the negative w squared over 2, and then dx becomes sigma dw. Well, the sigma here is going to cancel with the sigma squared over there, and we're left with an integral of the absolute value of w greater than or equal to sigma to the delta, 1 over square root of 2 pi, which doesn't really matter, e to the negative w squared over 2 dw. So this looks like a Gaussian integral. If I didn't have this restriction here, it would integrate to 1. It's the standard normal. What's nice is because we've adjusted it like this, I now can look at this, I can say, I'm integrating the standard normal, but starting very, very far away. So at this point now, it's clear that this integral has to go to 0, because as sigma gets very, very large, I'm integrating further and further down, and I'm avoiding all the main mass. So the question is just, can we approximate how rapidly this is decaying? Well, let's think about how we should do this. I want to break this up into different regions. So one possibility is, it's 1 over square root of 2 pi. Then I have the integral, and I'm going to multiply by 2, so I can assume w is positive. I'll have w goes from sigma to the delta to 1 plus sigma to the delta, e to the negative w squared over 2 dw, plus the integral w goes from 1 plus sigma to the delta to infinity, e to the negative w squared over 2 dw. The reason I want to break it up like this, and this is the reason I want to discuss this, is where is this integrand largest? So where's the integrand largest?
W equals 0.
When w equals 0. Well, we're not allowed to have w equals 0. So you're right, the integrand is largest when w equals 0, but I'm not considering w equals 0. So of the w that are in play, where is it largest?
W equals sigma.
Good, when w equals sigma to the delta. And so the further I go away from sigma to the delta, the larger w gets, the smaller this is. And this is getting small very fast. Let's think about what's going on over here. Is there much of a change in the integrand going from sigma to the delta to 1 plus sigma to the delta? So does this integrand change that much if I move by 1 unit, if sigma is large? If sigma is large, think of sigma as 10 to the billion. Even if delta is small, like 1 over 1,000, this is still going to be an enormous number. So the amount that I've changed is so insignificant here. Or maybe not. Look at the cross term. If you move 1 whole unit, look at the probability in the normal distribution when you go from 2 standard deviations to 3 to 4, the probability is dropping off pretty fast. There is going to be some decay going from here to here. I am going to be making a little bit of an error. You can actually approximate how much the error is. The smaller window I take over here, the better things are going to be. Maybe if I really want to get exactly how big this integral is, this would be a good problem. Maybe I take something of width, maybe like 1 over delta, or 1 over sigma to the delta, something really small. Because when I look and see how much things move by, I go from sigma to the delta to sigma to the delta plus 1 squared. And I square this. So when I square this, I'll get something like this, sigma to the 2 delta plus 1. And so if sigma to the delta, just sigma to the delta. If sigma to the delta is large, I actually have moved a significant amount. So maybe I shouldn't move as much as 1 unit. If I really wanted to understand how big things were, it might be better to instead go to sigma to the delta plus what? What would be a safe amount to move? If I do something like 1 over sigma to the delta and square that, that would get me sigma to the 2 delta plus 2 plus 1 over sigma to the 2 delta. And now when I move between the two endpoints, I've now not changed things by too much. In the other one, I've had a huge decrease. So again, you want to get a sense of how big these things are. How much am I leaving on the table by making these approximations? If I need a really accurate bound to do this is a bit wasteful. But I've already got enormous decay. I mean, when I'm putting in w equals sigma to the delta, I've got an e to the negative sigma to the 2 delta over 2. That's going to be damn small. And so I really don't need to worry about something like this. The size of this is so small, for most applications, you're not going to be that sensitive and that close that you really have to worry. But if you did, this is how you would do it. And this is why I want to spend the time going through how you attack bounds like this. When you need to be careful, this is what you start to do. You give yourself a little bit of freedom in terms of how far you move here, so that the integrand here is about the same size, and then you get a little extra decay over here. All right, so now when we do this, we can now approximate the first piece. So I can approximate the first piece by just using the value of the integrand at the very beginning. So this will be less than or equal to 2 over square root of 2 pi. Then the first piece will be an e to the negative sigma to the 2 delta over 2. And now for the second piece, I'm going to change variables. And I'm going to let u equal w plus 1. Or maybe there's a lot of different ways of doing this. What's the best way to do it? Yeah, go there. I'll have u go from 1 to infinity of e to the negative sigma to the delta plus u squared over 2 du. Yeah, it's fine to do it like this.
2 over 2?
I'm sorry?
Did you write 2 over 2?
2 over square root of 2.
No, the e to the negative sigma.
To the 2 delta divided by 2.
The next one?
Plus integral u goes from 1 to infinity e to the negative sigma delta plus u squared over 2.
Okay.
Right? We're still squaring everything. And so now when I look at this, I know w is going to start off at least as size sigma to the delta, and I want to see a little bit how much more is it going to get. And I want to get a sense of how big is this integral. So the first one is no problem. It's e to the negative sigma to the 2 delta divided by 2. It's not really worth my time getting too good of an estimate of the second if it's significantly smaller than the first. Right? I can do a really good job estimating this, but if this error is dwarfed by this one, if this one is much larger, it doesn't really do me much good to get a much better read here. So we can afford to be a little bit crude. So let's look at the second one, and let's see what we get. So in that one, we would get integral u goes from 1 to infinity. Let's expand. We get e to the negative sigma to the 2 delta plus 2u sigma to the delta plus u squared divided by 2 du. So I can pull out an e to the negative sigma to the 2 delta over 2. And then I have an integral u goes from 1 to infinity e to the negative u sigma delta e to the negative u squared over 2 du. And now I want to figure out how big is this integral. Well, notice I already have outside a term of the same size as what I had before. So as long as I can show that this isn't that large, it doesn't really pay to do a good job estimating. Okay? So unlike all your other classes, you don't have to do a good job. Half-assed, sloppy, perfectly acceptable here. Can anybody give me an estimate for how big this integral is? And you can be off by a constant. Can anybody tell me within a factor of 100 how big this integral is? Or at least be sure that the integral is not larger than that. What's a good upper bound for this whole integral? What do you think?
E to the minus sigma
So one possibility is, well, look, u's got to be at least 1. So this is going to be weighted by an e to the minus sigma delta. If I just pull that out, if I put it in its largest possible value here, I'm left with what looks like a Gaussian integral, except I don't have the 1 over square root of 2 pi. So I can just from this get that it's going to be at least, going to be at most square root of 2 pi times e to the negative sigma delta. So this will be less than equal to e to the negative sigma delta times square root of 2 pi. What you can see from that is that it's not worth trying to do a good job estimating this. This is already going to be significantly smaller than the other term, not worth playing the game at all. We could try to do a little bit better job, and we could say, well, let's integrate this exponential. We can maybe use the Cauchy-Schwarz inequality. And if you do something like that, you're not going to make any real savings, unfortunately. Okay. I have to, well, I can't take this right now. All right. So any questions on how we would handle this? All right. I want to do one more problem like this where we're doing estimates just because this is such an important concept. And so, in the book, I just go through the calculation. I don't really go into too much detail about how you think about these calculations. I really want to go through how you would approach these so that if you're ever doing any research with analysis where you need to get estimates like this, you know where to spend your time. And again, ideally, what you would do is you would replace the 1 with a free parameter. Over here, I have sigma to the delta. It was coming from a sigma to the 1 plus delta. That's really sigma times sigma to the delta. More generally, you would write it maybe sigma times g of sigma. And you would try to understand things in terms of g of sigma. And you would often play games and see how much do I need, how large do I have to let things go. In some sense, the larger you make this, the easier it's going to be to show that this is small, because you're going further down. But what that might mean is if you make this very large, you have more terms to consider for something else. And when you're doing the estimate, the more terms you have for something else, you might have estimates that don't work in that large region. So you're going to be splitting the problem up typically into 2 regions. You'll have different techniques in each. This, I have rapid decay, but the larger this is, the more terms I have to consider for the other. Okay, any questions about this integral? Okay, so what I want to do now is I want to do a little bit about counting primes. And so we will probably get to a proof of the prime number theorem or a sketch of the prime number theorem later. So counting primes. It turns out it's very convenient to define this function called lambda, which is going to be log p if n is a prime to the kth power and 0 otherwise. And the main fact we have, and this is essentially the prime number theorem, is that if you sum lambda of n for n at most x, this is approximately of size x. Once you have this, it's not too bad to deduce the prime number theorem. Let's take a look and see what this looks like. This is going to be the sum over all primes less than or equal to x of log of p plus the sum of p squared less than or equal to x of log p plus dot, 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 dot. So we have a bunch of terms like this to look at. This is the main piece. That's the piece we care about. We want to understand how many primes there are. Unlike other departments on campus where I can get into trouble, I cannot get into trouble for discriminating in the math stats department, so long as I do it within reasonable bounds. Okay? Is a log p weight bad? Does this vary greatly? If you go from x to 2x, if you double your range, the weight goes from log of x to log of x plus 2. If x is enormous, the log of x and the log of x plus 2 are essentially the same. There's really not much of a problem. If you go from x to x factorial, yes, in a range like that, you will see a difference now in these log rates. You go far enough, yes, you will see a difference. But the log function grows so slowly, you can go over large stretches. You can double, you can square your region, and you're not going to see much of a difference. Well, okay, if you square, you will see a difference. You'll go from log x to 2 log x. It'll still be the same order of magnitude at least. This is the main term we care about. These others, these are the error terms. And we want to see how large are they. So we want to understand the error, which is the sum p less than or equal to x, p squared less than or equal to x log p plus the sum of p cubed less than or equal to x log p plus dot 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 plus the sum p to the k sub x less than or equal to x of log of p. And I want to understand a sum like this. Well, the prime number theorem is going to tell us the number of primes at most x is about x over log x. This is a beautiful result. Can anybody give me a trivial bound for how many primes there are at most x? X. You know, thank you for not saying x squared or x cubed. Right? That would also work, but we can do a little bit better. This is yes?
Root x?
Root x primes at most x? No, for this one, yes. When we apply it here, we would get root x. But if I just want to count how many primes are at most x, it's root x. I'm sorry, now you got me confused. If I want to count how many primes there are at most x, it's at most x. Now, that means every single number would be prime. This is clearly an overestimate, but for a lot of purposes, this overestimate is fine. You know, you're going to be differing by a logarithm. It's not huge. Now, some problems are delicate enough that being off by a logarithm will kill you. I want to show you over here how much this really matters. Let's try to estimate the contribution here. Well, I can take all of these log p's and replace them with a log of x. And now this is the same as p less than or equal to x. This is the same as the sum of p less than or equal to x to the 1/2 of 1 plus the sum of p less than or equal to x to the 1/3 of 1 plus the sum of p less than or equal to x. What's the highest exponent I can take for k? So the best is if p equals 2. The smallest prime would give me the highest power. So if p equals 2, I can go all the way up to the log of x base 2. So I go all the way up to 1 over x to the log base 2 of x of 1. And I want to understand how large this is. Well, this is less than or equal to the log of x. This sum over here is at most x to the 1/2. The next sum is at most x to the 1/3 plus dot 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 plus x to the 1 over log base 2 of x. And now I want to figure out how large is this sum. So how would you estimate this sum? What would we do to estimate that sum? So can you give me a bound for how large this could be? So we want to bound x to the 1/2 plus x to the 1/3 plus x to the 1 over log of x base 2. What would be what's a good estimate for this, or what's an easy estimate? It's less than or equal to what?
The last one.
Okay, so we have log base 2 of x terms, and what's the largest term? It's not the last. X to the 1/2. So that's one estimate. With almost no work, you can do a little bit better. Or it's less than or equal to x to the 1/2. Take the first term by itself. And now look at the remaining terms. How many terms do I have left? Yes, exactly. Forget about the -1. Right? It's a pain to have to write that. It wastes chalk. Right? I need that money to buy M&Ms. Okay? So we're doing almost no additional work. I save a logarithm in my error term. And the reason is I'm throwing the error into two parts. The main term, which comes from the first, and then everything else. This is very similar to what we just did with the integral, where we split up the integral and we looked what was going on in that first little bit, And once we understood what was going on there, the remaining part was so much smaller it didn't matter. This is a general principle. Here is another example of that coming into play. And we can see here that all this stuff over here, it's x to the 1/3. If x is huge, x to the 1/3 is so much smaller than x to the 1/2, it doesn't really matter. Could we have summed all the way up to infinity? No, why couldn't we move the sum all the way up to infinity? What happens as we take larger and larger roots of x? What's it going to approach? It's going to approach 1. And so if we had the sum going all the way up to infinity, we would actually have the estimate that it's at most positive infinity. Well, correct, not useful. So you've got to be careful sometimes, how far can you extend things? So there is a limit to how far we can extend this, but we can extend it far enough so that we're okay. Okay, any questions about this argument? Okay, so as you can probably tell, this is a type of estimation that I really like. This is one of the reasons why I've become an analytic number theorist. I like calculations like this, it makes me happy. When you talk about morphisms and homomorphisms and group mappings, I'm not as happy. All right, where do we use this? We use this when we were studying Benford's law. So we were trying to prove that a geometric Brownian motion became Benford. And what's a geometric Brownian motion? It's a process whose logarithm is normally distributed with growing variance. And so the idea is if the variance is growing, let's have a quick plot. So here is a normal, here's a normal with slightly larger standard deviation, here's a normal with even larger standard deviation. When you look at this modulo 1, it's becoming the uniform distribution. So a normal distribution with mean 0, variance sigma squared, mod 1, is converging to uniform on 0, 1 as sigma goes to infinity. And so one of the papers I posted was a paper I wrote, I think with a colleague many years ago, proving that this converges to the uniform distribution, and from this we get Benford. Okay, so the main calculation is what happens if I look at a Gaussian. And I want to see if the Gaussian has very, very large standard deviation, what does it look like modulo 1? Does that look like the uniform distribution? Or another way of saying it is, does it become equidistributed mod 1? So how often mod 1 should I be in the interval AB if it's becoming equidistributed? That should be going to B minus A. So let's see if that's working for the standard normal. Although, obviously it can't be the standard normal because I need the standard deviation to be growing larger. There are many different normalizations you can use. I'm going to choose to use, all right, so we'll call it spreading Gaussian. I'm going to let Pn of x be n to the minus 1/2 e to the negative, I think it's pi x squared over n. Yes. So if you want, you can try to figure out exactly what is sigma, what is mu. So mu would be 0, sigma would be, multiplied by 2, it would be n over 2 pi square root. So it's on the order of square root of n. And the reason is the exponent is supposed to look like e to the negative x squared over 2 sigma squared. So I want a 2n down below, so I put a 2 up here. The 2 pi comes down in the denominator. The main thing is that the standard deviation looks like square root of n. Why am I doing this? It sets myself up very nicely for Poisson summation. And so for Poisson summation, basically, we'll get Pn hat at n will be e to the negative pi n squared n. And just make sure I'm doing it correctly. Yes. Okay. So the idea we're going to eventually use is the sum over n of Pn of x is the sum over n of Pn hat of n. This is Poisson summation. It's going to turn out that something like this is going to be related to calculating the probability that our value takes on something between a and b mod 1. And to understand this sum is the same as understanding this sum. So before going into all the details, I want to give you a sense of why this is going to work out. On this side, I'm going to get a sum over n of 1 over square root of n, approximately, e to the negative pi n squared divided by n, and this is the same as the sum over n of e to the negative pi n squared n. About how many terms do I need to care about on this side, on the left-hand side? How large can little n be and have this term still contributing? Root big N, or maybe a little bit more. So as long as little n is less than square root of n, so as long as n squared is less than big N, I'm going to have something that's going to be e to a very, very small number. E to a very small number is essentially e to the 0. E to the 0 is 1. So as long as n squared is less than or equal to n, terms are approximately 1. So they're all about the same size. So I'm going to have a huge number of terms. I'm going to have at least square root of big N terms. And if I start going a little bit beyond square root of n, then the terms start to decay. By the time I get to square root of n log big N, it's going to be small. Because then I'll have an e to the negative pi log n squared. That's going to be a small number. If I go even further, if I go up to like big N to the first power, or even more than to the first power, to the 5/4, it's going to be negligible, because I'm going to have a huge exponent up here. So really, once I get beyond square root of n, these terms don't matter. How about this side? How large must little n be before these terms don't matter? It's tough to say it without smiling. 1! The only term that really matters is n equals 0. Else, at least e to the minus pi n. If n is huge, that is really small. This is the advantage of Poisson summation. Which would you rather do, square root of n terms or 1 term? This is like the deal of the century. All right? Let's try to estimate how big the error would be. So again, I'm trying to just motivate right now why we would want to argue along these lines, what we're going to gain from doing all this. So if we want to study the sum absolute value of n is greater than or equal to 1, e to the negative pi n squared n. All right? This is going to be twice the sum n goes from 1 to infinity, e to the negative pi n squared n. One thing I can do is I can drop the square. If I drop the square, I'm just making my error terms much, much larger. So this would be less equal to 2 sum n goes from 1 to infinity, e to the negative pi n n. Well, that's a geometric series. And so I'll get 2 e to the negative pi times big N over 1 minus e to the negative pi n. Was this a hard or an easy bound to do? I'd say easy, right? What's the question you should be asking yourself now? We just made an estimate. Is it a good enough estimate? Is it wasteful? Right? How much am I throwing away? How much are we leaving on the table by doing this? How should we break up this sum? How should we view this sum? What should we do?
First term.
Excellent. First term, e to the negative pi n plus the sum n goes from 2 to infinity, e to the negative pi n squared n. Well, just looking at the first term, we've got a 2e to the negative pi n, 2e to the negative pi n. If n is huge, the denominator is essentially 1, right? The amount that we're overestimating by, the amount we're changing by, is negligible. And now let's look at what's remaining. Yes?
When you sum the geometric,
Did I make a mistake?
doesn't it start at 1
Yes?
instead of 0?
Yeah. That's why we have something in the.
Oh, okay.
That's why we have something upstairs. Yes. So if we look at something like this, the main term here is essentially the same as the main term here. They're really the same. They differ by a very small constant. How could we estimate this stuff over here? How could we estimate all this?
Same thing as before.
Same thing we did before. So drop the square. And if we drop the square, then we'll have an e to the negative pi times 2n. Or we could be a little bit cleverer. Not enormously cleverer, but even a small amount. We could say, hey, look, this is going to be less than or equal to the sum of e to the negative pi n. N goes from 4 to infinity. Because I've got, my terms are 4, 9, 16, 25. So why drop the square and make everything 2, 3, 4, 5? Why not just drop the square and go from 4? If you do that, you see you're going to get an e to the negative 4 pi n, enormously smaller. Is it harmful to make this estimate and use the geometric series? Is it worthwhile to try to figure out exactly how big this sum is? No. Okay? So probably the best thing I can teach you is what not to do in life. Okay? This is not worth spending your time on. You're going to be spending your time on errors that are so small and insignificant that you will not be able to notice them. It's not going to help you to get a better estimate for this tail. This tail is way beyond anything you're going to see. So it's not worth trying to study. Okay. So let's come back over here. We've got all the setup over here. Now what I want to do is I want to study the probability I take on a certain value. Do you want me to leave the stuff over here and just work on the next board, or can I erase the stuff on the bottom? Okay. And so what we want to do is we want to calculate the probability that my random variable x mod 1 is in AB. And I'll put a subscript n over here to remind myself that this is coming from my process. So this is going to be an integral. Let me do it this way. A sum, n goes from minus infinity to infinity. I'm going to go from a plus n to b plus n, the probability dx. Right? Okay, so this is what I have. So let's try to figure out how big this is going to be. Do I have to be careful about the order of the sum and the integral? No. Why don't I have to be careful?
It's always positive, so it's absolutely convergent.
Always positive, absolutely convergent. The Gaussian decay is really fast. We're not worried at all about convergence issues. All right, so now we want to sum. N goes from minus infinity to infinity. Integral from a to b, I'm going to write it this way. 1 over square root of n, e to the negative n plus x squared pi divided by big N dx. All right, well, x ranges from a to b, x is at most 1. When little n is really large, do we agree that the contribution is negligible? So we can throw away the absolute value of n is big. All right, what should we use to measure the size of big? It's got to be at least how big? So how large must little n be before I'm sure that this is going to be small? It's got to be at least root n. Okay? If it's root n, I am living life on the edge. Right? I'm just at the cusp where everything is working. Do I want to be careful? Have you seen me give a careful well thought out lecture yet this semester? No. I don't want to spend time carefully calculating things. I want to be lazy. I want to be crude. I want little n to be larger than square root of n. So I will take n in absolute value to be greater than or equal to n to the 5/4. This is excessive. I mean, this is living a life of luxury, right? You should view this as, square root of n times n. Okay, square root of n would be 2/4 times like 3/4. I mean, boy, this is way beyond, what I need to be. It's fine to be this large. Okay, so, if I take my n to be this large, I don't have to worry about the contribution from those. And so I can restrict the sum to just being up to small n. And so now we restrict the sum to n less than or equal to n to the 5/4. All right. If n is not that big, I can approximate how much this is changing. And this is where we do a simple Taylor series. For such n, e to the negative n plus x squared pi over n is approximately e to the negative n squared pi over n, 1 plus, and I think it's the maximum of the absolute value of n, and I think 1, yes. Now let's see, unfortunately the camera doesn't come back. So I have to go like this and go, hello camera. No, that's not enough. Okay, so you can walk like this. The old-fashioned way. All right, so maximum of n, 1 over big N, e to the negative n squared over n. So I'm being a little crude over here in terms of using the Taylor series. The main thing is I want to write things in terms of the value of my function at the end. If x is only going in a region of size 1, this thing is not going to be moving that much. And I can just take the derivative, I can expand. I want to evaluate things in terms of the left endpoint. Now when I look at this ratio, if little n is much larger than n, is this factor in front going to bother me? So if little n is as large as n to the 5/4, is this going to be troublesome? This factor in the front. Just looking at the factor in the front, if little n is larger than n, if it's like n to the 5/4, is that a bad factor? Is it big or is it, yeah, it's big. It's going to be a problem. But if n is large, this factor here is significantly smaller. Once n hits square root of n, this factor is of size 1. Once n starts getting larger than that, we're going to be greatly protected. So as little n starts approaching n, this is looking like n squared over n. And it's going to be very, very small. So I don't have to really worry that this is going all the way up to n to the 5/4. Okay? So in terms of my estimate like this, the contribution from these pieces is going to be negligible. I've got an extra n down below here. And this part over here is not going to be bad. So in the book, I go through the calculation that this piece doesn't really matter. Right? I'm not going to do that now, but you can Taylor expand. This piece will not matter. All right, and so now what we do is we have our sum over all n less than equal to n to the 5/4. This is going to be approximately the sum of n less than equal to n to the 5/4, the integral from a to b, e to the negative n squared pi over n dx. This is the easiest integral I can give you. What's the value of this integral? What would be the value of this integral? It's b minus a. I'm integrating a constant, right? I'm summing over n, but there's no x dependence. So each of these is going to give me, I'll have a b minus a, and then I'll have a sum n less than or equal to n to the 5/4, e to the negative n squared pi divided by n. All right, what does this look like we can use? It looks like, what's this looking like? Poisson summation. Why can't we use Poisson summation? It's finite. Fortunately, I can just erase that. So if we extend it to all n, okay, am I allowed to just erase the bound? Apparently, yes. It's wonderful being a math professor. Why can't I just replace this? All right, so I will keep it as n less than or equal to n to the 5/4. But this is the same as b minus a, the sum over all n, minus infinity to infinity, e to the negative n squared pi over n, plus small. And the reason is, look, once n is as large as n to the 5/4, the sum of those terms is going to be really small. You can bound it with a geometric series, lots of ways to approach. Because we're n to the 5/4, this is negligible. I don't even need to square things because I'm larger than n. So if you want a really good exercise, is go through this and try to figure out, if you really wanted to be careful, where would you put the cutoff values? I'm not even close to careful. Because I don't care. At the end of the day, big N goes to infinity. It might affect a little bit the rate of convergence. That's fine. And so now we use Poisson summation. And so this is b minus a times the sum over all n. Oh, I'm sorry. We have a 1 over square root of n. So I will have to restore the 1 over square root of n. 1 over square root of n. 1 over square root of n. And now we get e to the negative pi n n, pi n squared n plus small. And now from Poisson summation, the only term that matters here is when n equals 0. And then this becomes b minus a plus small. So again, you can now go through and you can carefully do the analysis. I want to give you the highlights. I want to give you the main ideas. The main idea is we start off with an integral. So we have an integral, n goes from minus infinity to infinity. So we're chopping us up into blocks, between n and n plus 1. Between 1 and 2, 2 and 3, 3 and 4, 4 and 5. And for each one, we look and see what fraction of the time are we in the interval ab mod 1. All right, so now what we do is we take our integrand here, and we see that we can expand it, and we can do a Taylor series approximation that's going to be pretty good. And this is going to work all the way up to really large values of n. So we can truncate the sum, Taylor expand, deal with the Taylor expansion because it's only a finite sum. Deal with that finite sum, get an error, and now we take what's left to the main term, and then we extend that sum back to infinity so we can use Poisson summation. Okay, so this is a good place to stop, and then I will...